Welcome back everybody to this fourth episode in the openStars video series. We're covering basic stellar astronomy, and as we go we are demonstrating important concepts by doing experiments using the Greystar 3 virtual star simulator. In this episode we are going to introduce a fifth and final basic property or parameter that describes stars. This time we want to introduce a property that describes a star's brightness, something we actually haven't talked about much yet in this video series. It's a basic property that we can observe about stars that they shine, they emit light or have a brightness. And you might recall back in episode 1 that we talked a little bit about why that is. But that's a very important idea, so let's just spend a little bit of time reviewing what we said. That the reason why stars shine, the reason why they have a brightness, is because they are dense, opaque objects that are hotter than their surroundings. They have excess heat, and in that situation it's natural for the hotter object to try to cool itself off by emitting energy in the form of radiation through its surface. Now you might recall that we said that radiation that's emitted by a dense hot object for this reason is what we call thermal radiation or incandescence. And remember also an important idea here is that light, including starlight, is a form of energy. It is radiant energy or radiation. So we're going to define a new term here, a new basic property of stars, namely a star's total luminosity. Now the word luminous is the root of that word luminosity, and as you may know, the word luminous means glowing, so this should make sense. And by definition, a star's total luminosity is the total energy in the form of incandescent or thermal radiation that's emitted by the whole surface of the star per second of time. So let me actually show this image as I'm talking about that. Okay, so note that the luminosity of a star is not just an energy, it's actually an energy rate. It's the amount of energy leaving the entire surface of the star per second of time. And as you may know, if you've had a little bit of physics, an energy per unit time is what we call a power. So a star's total luminosity is really its total radiation power or its total brightness power. And in metric units, the standard unit of power is the watt. So we can express total luminosity in units of watts if we want to be on the metric system. And you can think of a star's total luminosity as a wattage. It's the star's brightness wattage. Now I'm just going to let you know about another funny little piece of vocabulary here. In astronomy, astronomers refer to a star's total luminosity as that star's bolometric luminosity. So that word bolometric is sort of a funny word, but we can take it as just meaning total. In fact, let me go back over here to the Greystar 3 interface and just scroll down to the output panel. Over here on the left, Greystar 3 actually prints out the total luminosity of the star that it has simulated. And it's using the letter L here to stand for luminosity, and the subscript bol here, BOL, stands for this word bolometric. So this is the bolometric luminosity that's being printed out here, but that just means the star's total luminosity. In fact, what this word bolometric really indicates is that we are talking about the luminosity of the star due to light of all the different colors throughout the whole spectrum added together. But not to worry too much about that, when you hear the term bolometric luminosity, you can just think total luminosity and we'll have the right idea. This idea of expressing the brightness of a glowing object in terms of power in units of watts should sound familiar to you. After all, this is the same way that the brightness of household light bulbs is rated. If you go shopping for light bulbs, then the brightness on the packaging is rated as being, say, a 60-watt light bulb or a 100-watt light bulb or something, and the same thing is going on there. They probably don't use this terminology on the packaging, but that wattage is the light bulb's total luminosity, and it has exactly the same meaning that it does as in the case of stars. So we know that for household light bulbs, the kind of brightness power we're talking about is something like 60 watts, say. What about the sun? The sun's total luminosity is 4 times 10 to the power of 26 watts. So that's 4 followed by 26 zeros, or 400 trillion watts. And that's equivalent to 6.5 trillion 60-watt light bulbs. So the sun is a pretty luminous object. And of course, that's why you should never go outside and actually try to look directly at the real sun in the sky. Right? Not even once, not even for a second, not even with the most expensive sunglasses money can buy. It's just far too easy to damage your vision permanently very quickly looking at an object that's that luminous. So you can see that we're going to have the same problem when we talk about the luminosity of stars that we did back in episode 2 when we were talking about mass and radius. Namely, that if we try to do it on the metric system, we're going to get these really big numbers that are kind of awkward and really don't mean very much. So we are going to take care of this in the same way that we did with mass and radius, namely by introducing solar units. So if you followed episode 2, this should sound like a pretty familiar story by now, and you should be able to guess what we're going to do. What we're going to do is introduce a new unit of power, namely the solar luminosity, where by definition, one solar luminosity is whatever luminosity, total luminosity, the sun happens to have. Okay, so in this system of solar units, the sun's total luminosity by definition is exactly one solar luminosity. And we can use this unit to express the total luminosity of other stars, and that will be more meaningful. So if I tell you, for example, that we have a star whose total luminosity is, say, 2 solar luminosities, that immediately tells you something meaningful. It tells you that that star's total brightness power is twice that of the sun. But of course, the price we pay for using solar units is it means that we are no longer on the metric system, we are in the system of solar units. Before we go any further, we should take care to make an important distinction between two fundamentally different ways of defining and thinking about brightness. Namely, we should take care to make the distinction between absolute brightness and apparent brightness. The property that we're talking about in this episode, the total luminosity of a star, is an intrinsic property of that star itself. Or another way to think about it, it's a fundamental parameter of that star. That is to say, total luminosity only depends on the nature of the star itself. In particular, total luminosity does not depend on any details of an observer who may be trying to measure the brightness of that star. In particular, it does not depend on the distance that an observer might have from a star. So for that reason, luminosity is also referred to as absolute brightness. And the advantage of that definition is that it is unambiguous. On the other hand, though, what this also means is that luminosity is not a quantity that we can directly measure from our location here on Earth. In fact, if we think about the definition of luminosity that we gave earlier, the only way to directly measure a star's luminosity would be to completely surround that star with a hollow sphere of light detectors all pointing inwards, so that these detectors capture every little bit of radiation power coming out of the entire surface of the star going in all directions. That would be the only way to directly measure a star's luminosity or absolute brightness. The other definition of brightness for us to think about is apparent brightness. The apparent brightness of an object corresponds to the radiation power that an observer some distance from the center of the object would intercept with a detector. Now keep in mind that this detector that we're talking about could be the aperture of a telescope or a camera that's focusing light on a detector, or it could be the pupil of the human eye. Now, this brightness that an observer some distance away intercepts with a detector is what we call the flux. So the flux is the quantity that expresses apparent brightness. And of course, it's the flux, or the apparent brightness, that we can measure from our position here on Earth. So the important thing is that unlike luminosity, the flux of a star does depend on the observer's distance from that star. That for a star of a given luminosity, the greater its distance from the observer, the smaller the flux will be intercepted by a given detector, and so the smaller will be the apparent brightness of that star. In fact, the relationship between the distance to a star and its flux, or apparent brightness, is an inverse square law. That if we have a given star with a fixed luminosity, and we measure it, say, at this first distance away with a given detector, and we measure a certain flux, and then if we were to double our distance back to here, the flux that we measure from that same star would drop to 1/4 of what it was before. That we've doubled our distance, and 2 times 2 is 4, so the flux would fall by a factor of 4. And if we were to triple our original distance and come out to here, the flux that we would intercept from that star would be 1/9 of what it was at the original position. That 3 times 3 is 9. So that's an inverse square law, and that's really just due to geometry. In fact, if you think back to episode 3, we also saw that the force of gravity from an object like a star also follows an inverse square law. Now, we've actually talked about flux before. If you think way back to episode 1, when we were talking about photometry and measuring the color of a star, the brightnesses that we were measuring through filters of different color, those quantities were fluxes, just like we're talking about here now. It's important to remember the ambiguity of flux or apparent brightness when you look at an image like this one. And again, this is just an image of a star field taken with the Hubble Space Telescope, taken from the Hubble Heritage Archive. And when you look at an image like this one, where they have imaged the point sources corresponding to stars, the brightnesses that you see in this image are fluxes or apparent brightnesses. They are not luminosities, and that raises an ambiguity of interpretation. So just to see what this means, let's pick on a particular star. Let's pick on this star right here that is relatively bright in this image. It has a high apparent brightness compared to the other stars in the image. There's at least a couple of different explanations for why that could be. One explanation is that maybe this star is very far away from us, that it may be much more distant from us than most of the other stars, but it may be that that star has a relatively large luminosity or absolute brightness. And so that's why it has a large apparent brightness, even though it's relatively far away. Or, on the other hand, another possible explanation is that maybe this star actually has a relatively small luminosity or absolute brightness, and it just happens to be very close to us compared to all the other stars around it, and that's why it shows up with a relatively large apparent brightness in our sky. We just don't know which it is, or it could be some combination of distance and luminosity that's in between those two extremes that conspires to give this star a relatively large apparent brightness. And by contrast, if we were to pick on, say, a relatively faint star, one of these relatively faint ones in this image, again, we don't know why that star has a low apparent brightness. We don't know if that's because the star has a very low luminosity or absolute brightness, or if it's because the star is very, very far away from us compared to the other stars. We just don't know. That you don't know a star's real luminosity from an image like this one unless and until you measure the distance to that star. So now it's time to start doing some experiments with the Graystar 3 virtual star simulator. So what we want to do here is we want to do some experiments that will help us to understand a star's total luminosity. Now, as before, I'll just remind you that in this top control panel here, the one that's got the green background color, that's where we will find all of the input controls that let us specify the basic properties that will determine the star that we are simulating. So the first thing you may notice is that we do not have a total luminosity knob here, that there is no control that we can adjust to directly set the star's total luminosity. Now that's actually a clue to what we're going to find. What we're going to find is that if we want to control a star's total luminosity, we're going to have to do it by adjusting a couple of these other basic parameters that we've already talked about. Okay, the next thing I'm going to remind us of is that by default, when Graystar 3 first loads, it is simulating the sun. So that means that all these input parameters here have been preset to their values for the sun, and down here it is the sun that we are simulating. So we can just do a little reality check here before we go any further, that the computed luminosity of this model should be exactly 1 solar luminosity. And remember something we talked about earlier, Graystar 3 is reporting down here in this panel what the luminosity is of the star that it is simulating. That's this quantity symbolized with L subscript ball for bolometric luminosity or total luminosity. And that's being reported in solar units, units of solar luminosities. And you can see that there's something here that's not quite right. That the star we're simulating doesn't quite have the sun's luminosity. If it did, then this value should be exactly 1 solar luminosity. It actually isn't. It's a bit smaller than that, more like 0.88 solar luminosities. And for that matter, if you come up here and look at the reported radius of the simulation, you can see that it's also a little bit too small. It ought to be exactly 1 solar radius, and instead we're getting this slightly smaller value of 0.933. So the simulation is a little bit too faint and a little bit too small to exactly match the sun. So now we could say, well, maybe the simulation just isn't very accurate, but these numbers are sort of close enough to 1, so we could just not worry about this and carry on with our experiments. But we can actually do a little bit better than that. So I'm going to let you know what's going on here, and this will also give me an opportunity to tell you about another quirk of how Graystar 3 works, especially for those of you who are teachers planning to use this. So let's go back up here to the input area. And to tell you the truth, what's happening here is that these values for the sun's effective temperature and surface gravity are not really the exact values for the sun. What they are is the nearest round values. So what's happened here is that the effective temperature has actually been rounded up from the sun's exact value to the nearest whole number multiple of 100 Kelvin. And the surface gravity here has been rounded up from the sun's exact value to the nearest whole number multiple of 0.5 in the log g. And that's actually why we're getting results that are not quite right for the computed radius and luminosity of the sun. So let's see if we can fix this up and do a better job here. So what I'm going to do is put in more accurate values for the sun. I'll let you know that the sun's exact effective temperature is more like 5778 Kelvin. So I can set that exactly by just typing it in here. And the exact value of the sun's surface gravity is more like 4.44 in the log g. Okay, so with these more exact values, we ought to do a better job of simulating the sun's exact radius and luminosity. So let's come down here and just look at the reported radius and the luminosity. Maybe I'll zoom in a little, and we'll see what happens when I hit the model button. Okay, so you can see that the radius and the luminosity have changed a little bit now that we've adjusted these parameters, except now we are a little bit too large and a little bit too bright. We're now getting a radius that's a little bit bigger than one solar radius. Maybe it's a little closer than it was before, but now it's a bit bigger. And we're getting a luminosity that's now a bit too bright, 1.1 solar luminosities. So that's not much better than what we were getting before. So things still aren't quite right here. And if we go back up to the input panel, you can see what's gone wrong. In fact, maybe you could already see it before we even went down to the output section. You can see that Graystar 3 has actually clobbered our exact input values, that we put in a value of 5778 for the sun's exact effective temperature. And right away, before we could do anything, Graystar 3 actually clobbered that and turned it to 5780. That's because Graystar 3 wants the input effective temperature to be a whole number multiple of 10 in order to simplify how this input knob works. And it also clobbered our value for the surface gravity. It turned it down from 4.44 to 4.4. That's because Graystar 3 wants the input surface gravity in log g to be a whole number multiple of 0.1. So Graystar 3 is just not going to let us set the exact values for the sun's effective temperature and surface gravity, and so we're never going to be able to exactly hit the sun's total luminosity and radius here with our simulation. The simulation's always going to be a little bit off. So we may as well go ahead and just go with the default values, and I can get those back, remember, by hitting reload. So we are back here to the values of 5800 Kelvin and 4.5, which aren't quite right, but we may as well take them anyway and work from there. So this is just a little quirk of how Graystar 3 works that's worth keeping in mind, particularly for those of you who are using this in teaching. Okay, so let's go ahead and do some experiments now to determine which of these fundamental input parameters will control the total luminosity of the star that we are simulating. And just to give you a little sneak preview of the answer here, there are actually two of these input parameters that both control the total luminosity. And the first one that we're going to talk about is the effective temperature, which you might remember is something that you can really think of as being the surface temperature of the star. This is the parameter that we talked about way back in episode 1. So we're going to do some experiments though to find out exactly how that works. But before we do that, we better just check to make sure that we are in our initial position here, modeling our primary reference object, the sun. So we are at the sun's effective temperature here of 5800 Kelvin. And if I come down to the output section, we are modeling a star. The simulated luminosity is a little bit less than one solar luminosity, about 0.88. Okay, so let's just keep that value in mind, that that's the reference value that we want to compare to. So I'll come back up here to the input section. I'm just going to zoom in here so we can see things more clearly. And I'm going to grab a hold of this effective temperature knob, and I'm going to turn it all the way down as low as it will go to 3500 Kelvin. I'm just going to type that in here so I can be exact. So there's 3500 Kelvin. So let's come down here to the output section. I'm going to hit the model button, and what we want to do is just keep our eye on the computed luminosity of the simulation. Okay, so here we go. All right, so now we are simulating a star whose effective temperature is 3500 Kelvin, and you can see what's happened to the computed total luminosity, that it has fallen to a value of about 0.12 solar luminosities. So that's somewhere between 1/8 and 1/9 of a solar luminosity. So you can think about that a little bit. If we turn down the effective temperature by less than a factor of 2, from 5800 to 3500 Kelvin, then the total luminosity falls by a factor of somewhere between 8 and 9. Okay, now before we think too much about this though, let's explore the other end of the range. So I'm going to go back up to the top here and turn this effective temperature dial all the way up as high as it will go to 25,000 Kelvin. Okay, 25,000 Kelvin. We'll come down here and hit the model button and keep your eye on the total luminosity of the simulation. Okay, and you can see what's happened. We're now simulating a 25,000 Kelvin effective temperature star, and its total luminosity has shot up to a little over 300 solar luminosities. Okay, so putting it all together, what we've just done is we have just increased the effective temperature by a factor of 7. Okay, going from an effective temperature of 3,500 Kelvin to a value of 25,000 Kelvin, that's an increase of a factor of 7. Now, what happened to the total luminosity? It increased from a value of somewhere between 1/8 and 1/9 of a solar luminosity up to a value of about 300 solar luminosities. So that's an increase of about 2,500 times. Okay, so let's just put those two facts together here. If you increase the effective temperature by a factor of 7, the total luminosity goes up by a factor of 2,500. Okay, so total luminosity seems to depend very sensitively on effective temperature. And in fact, we know that the exact mathematical relation is that a star's total luminosity varies as its effective temperature to the fourth power. Okay, that's effective temperature raised to the power of 4. So we can just kind of check that out and see if that agrees with the experiment that we just did. We increased the effective temperature by a factor of 7 from 3,500 to 25,000. So a first power of 7 times a second power of 7 is 49, times a third power of 7 is 343, times a fourth power of 7 gives you 2,400. So 2,400 is a little bit smaller than the factor of 2,500 that we found for the increase in the luminosity. But remember, our simulations here are a little bit approximate. The fact is that we know that the precise relationship is that a star's total luminosity goes as its effective temperature to the fourth power. Okay, so just to think about an easier example here for a minute, if we were to take a star and increase its effective temperature by a factor of 2, how would its total luminosity change? It would not just increase by a factor of 2, it would increase by a factor of 16. Right? 2 times 2 times 2 times 2, 4 factors of 2 multiplied together to give you 16. And that also goes in the opposite direction. If we were to take a star and turn its effective temperature down by a factor of 2 so that it's half the value it had before, what would happen to its total luminosity? It would fall by a factor of 16 to 1/16 of what it was before. All right, that 4 factors of 1/2 multiplied together give you 1/16. Okay, so it works both ways. So the conclusion that we can draw is that the total luminosity of a star is a very sensitive function of its effective temperature. That if you change the effective temperature just a little bit, the total luminosity is going to change by a lot. You get a lot of bang for your buck. And that's just the nature of thermal radiation or incandescence. Well, I promised us a couple of minutes ago that there were actually two basic stellar input parameters that control the star's total luminosity. The second basic input parameter that affects luminosity is the star's radius. But wait a minute, we do not have a knob here that controls the star's radius in the Gray Star 3 input control panel. And in fact, there's not supposed to be a control that affects radius directly. Something we talked about back in episodes 2 and 3. So what are we going to do? Well, this is okay because if you think about episodes 2 and 3 and what we talked about, then you'll realize that if we leave the stellar mass fixed, that its value of one solar masses, then the surface gravity by itself will affect the star's radius. So what we want to do in our experiments is just make sure we leave the stellar mass knob alone, so it's at one solar mass, and then we can control radius through the surface gravity knob. That the surface gravity is a proxy for radius in that sense. Okay, so let's make sure we reset ourselves back to our primary reference object, the sun. So I'm just going to hit reload here and we're back to the solar parameters. We are back to the sun's effective temperature of 5800 Kelvin. Now remember, we just learned in our last experiment that the star's total luminosity is also affected by the effective temperature. Okay, so we want to, in the spirit of doing controlled experiments, we want to make sure that we leave the effective temperature alone. We'll just leave it fixed at 5800 Kelvin throughout these experiments, and we will only adjust the surface gravity. Okay, so we are also back to the sun's default surface gravity of 4.5 here. So let's just remind ourselves of what the values of radius and luminosity are for our reference object here. We're back to values that are close to the sun's values, a little bit less than 0.1 solar radii and 1 solar luminosity. Okay, so when we do our experiments here, adjusting the surface gravity, remember that we're going to want to keep our eye on both of these numbers, that when we change the surface gravity, we first want to see how that has affected the radius of the star that we're simulating. Then, having taken note of that, we want to see how that's affected the total luminosity of the star that we're simulating. So that's how we're going to proceed. So let's come back up here to the input controls here, and let me start by turning the surface gravity here down as far as it should go. So I'm going to turn that down all the way to a value of 2.5 in the log G. Now, first of all, if we think back to what we talked about in episode 3, we can make a prediction. How do we think the radius of the star will be affected if we turn the surface gravity down, but from 4.5 to 2.5 in the log G? And what we should expect is that the radius will increase when we turn the log G down. All right, that the way you can think of that is that we are turning down the force of gravity that's trying to compress the star. So that one solar mass of material here that makes up the star is less compressed by gravity, and so it will puff out more, and the star will fill a bigger volume and have a bigger radius. The second thing here for us to remember is that at the sun's effective temperature of 5800 Kelvin, 2.5 is the lowest value that we should try to set for the surface gravity here. Remember that if we try to set a lower value for the surface gravity, then gray star 3 will just turn it right back up again to 2.5 for us. And that's because gray star 3 automatically protects itself from trying to model stars that would be unstable and crash the code. And at a temperature of 5800 Kelvin, 2.5 is the lowest stable value of log G. Okay, so having set our value of the input surface gravity here, let's go down and do our experiment. So before I hit the model button, remember that we want to keep our eye first on what's going to happen to the radius of the star, and then think about what that means for the total luminosity of the star. So here we go. So we're now modeling a star whose surface gravity is lower than the sun by a factor of 100. We've gone down by 2 in the log G, and you can see what's happened to the radius of the star, that it's increased to 9.3 solar radii. And if we wanted to, we could also see that increase in the radius in the image of the star that's being simulated down here, but the more precise way to look at it is by noting the printed value of the radius here. Now let's have a look at what's happened to the total luminosity of the star. It's increased to 88.4 solar luminosities. So if you are familiar with the squares of the whole numbers, then maybe you can already start to see here what the relationship is between total luminosity and radius. That it looks like the total luminosity is increasing as the radius squared. All right, that 9 squared is 81. 9.3 squared is going to be about 88.4. So it kind of looks here already as though we can tell that total luminosity goes as the square of the radius. But let's just do an experiment going in the other direction though and make sure of how things are behaving. So now let me grab this surface gravity knob and I'll turn it all the way up this time to the highest value it will go to, a log G of 5.5. So this time we should expect that we're going to get a star that's smaller than the Sun because we've turned up the force of gravity. That's going to compress the gas more into a smaller volume. But let's come down here and see what happens. I'm hitting the model button, and we can see that the radius of the star has increased to a value that's a little bit less than 0.3 solar radii. Okay, so with this stronger gravity, we're compressing the star down to less than a third of the radius it had at the solar surface gravity. And you can see what's happened to the total luminosity. That the total luminosity is now a little bit less than 0.09 solar luminosities. Now it turns out, so if we round the radius here to 0.3 solar radii, 0.3 squared is 0.09, and that's close to what we're getting for the luminosity. So once again here we're seeing the same thing, that the total luminosity of the star goes as the radius squared. All right, now to put together the two experiments that we just did, we just increased the star's radius by a factor of 31 over the range of these experiments. We went all the way from a radius of 0.3 solar radii all the way up to a radius of 9.3 solar radii. So that's an increase of 31, a factor of 31 in the radius, and the luminosity increased by a factor of 980, all the way from 0.09 solar luminosities up to 88.5 solar luminosities about. Okay, so 31 squared is about 980. So again, what we're seeing is that the star's total luminosity varies as its radius squared. Okay, so to take another example that's a bit more simple, if the radius of a star doubles, then how does its total luminosity change? It doesn't change by a factor of 2, it changes by a factor of 4. Okay, double the radius, the total luminosity would go up by a factor of 4. And then finally, we need to keep in mind that we have to put together both things that we just talked about, the dependence of the star's luminosity on effective temperature and on radius. Okay, that both of those things are acting at once, that a star's total luminosity will go as the effective temperature to the fourth power and as the radius squared. Okay, that both effective temperature and radius are together determining the star's total luminosity. So that concludes our discussion of the fifth and final basic stellar property that we're going to talk about in the openStars video series. So if we review everything, all the properties we've talked about, there are 5 of them. We've talked about effective temperature, which you can think of as a star's surface temperature. We talked about that in episode 1. We've talked about a star's mass and radius together in episode 2. We've talked about a star's surface gravity, which we express as a log G value. We talked about that in episode 3. And now finally, we've talked about a star's total luminosity in this episode, episode 4. And I just wanted to take a little bit of time in this episode to emphasize the significance and the usefulness of knowing about these 5 basic stellar properties or parameters and how they are related to each other, because we are actually now in a position to do some pretty serious astronomy. Now, the first idea that I'm going to emphasize here is that of these 5 basic stellar parameters, there are 3 of them that we can set as input parameters in the Graystar 3 virtual star simulator. Let me just hit reload here and escape back to the sun. Okay, now of those 5 basic properties we've talked about, why these 3 for the values that we can set as inputs? And the reason is because these 3 are the 3 that are the most measurable, the most directly measurable. Okay, and we talked about how to measure each of these 3 things, effective temperature, surface gravity, and stellar mass, in the first 3 videos in this series. The other 2 of the 5 parameters, radius and luminosity, are not as easily measurable. They are less directly measurable, and so we're going to treat them as quantities to be calculated by the simulation as opposed to being inputs that we can set, like the first 3 parameters. Okay, so that's actually quite important. That same approach is taken in any sort of computer program that simulates the observable properties of stars, that the input parameters that the user can adjust are always restricted to be those that are the most directly measurable for real stars. And that is how things are done even in more sophisticated computer programs that are used in astrophysical research. So now let's consider the following situation, which is a realistic one in astronomy. Let me go back to this Hubble Space Telescope image here, and let's say that we are interested in learning everything that we can about a particular star of interest. Let's say this bright red one here. Let me zoom in a little bit. Okay, so let's pick on, oh, here's a better one here. Let's pick on this star right here, say, where I've got the cursor. Let's say we want to learn everything that we can about that particular star. And we're just going to review things that we've already talked about so far in this series. So first of all, we could start off by doing some stellar spectroscopy, like we talked about in episode 3. So in other words, we could record the spectrum of the star, this thing right here. And by carefully noting the width of these dark features here, these spectral lines or dark lines, we can measure the star's surface gravity, its log G value. And that is something that we talked about in episode 3. So if we do that, that allows us to set the value of the second parameter knob here in a gray star simulation of that star. So let's say we've measured its surface gravity to be, say, 2.0. Okay, so now we can set the second knob for a model of that star. Okay, now let's say what's more, so here's our star of interest here, we're still picking on it. Let's say that we can also measure that star's mass. Let's say that that star is a member of a binary star system. And remember, binary star systems are quite common, so that's not an unlikely scenario. Then we could also measure the star's mass, and that would allow us to set the value of this third parameter knob here. So let's say its mass is 1.5 solar masses. Now already, if you think about what we talked about in episode 3, we already have enough information just by knowing the surface gravity and the mass to calculate the star's radius. But let's keep going. Thinking back to episode 1, let's say that we also do some photometry, that we measure the flux of this star or its apparent brightness through a set of colored filters so that we can measure that star's color and determine its effective temperature. That's something that we talked about in episode 1. If we were to do that, that would allow us to set the value of this first control knob here, the effective temperature. Now that was a pretty red star, and so as you probably know, that means that this star probably has a fairly low effective temperature, let's say 4,000 Kelvin. Okay, so at this point, we have now made enough measurements to be able to set the values of the first 3 parameters here, effective temperature, surface gravity, and stellar mass, in a gray star 3 simulation of that star. And so we could proceed and calculate a model. And there it is. There is a gray star simulation of that particular star based on our measurement of its three parameters that are the input parameters for a gray star 3 simulation. Now along the way here, that also means that we have been able to calculate the star's radius and its total luminosity. So that's pretty good, but things get even better, because by calculating the star's total luminosity, we have calculated its absolute brightness. Now, one other thing that we can always do, so let's go back and pick on our favorite star here. Something else we always have the option of doing is measuring the flux, or the apparent brightness of that star, intercepted by a light detector here on Earth. So if we measure the flux, or the apparent brightness of that star, and we also know its absolute brightness, or its luminosity, from the modeling we just talked about, then we can calculate the distance to that star. Remember that the flux, or the apparent brightness of a star, depends on a combination of its luminosity and its distance. We have fixed the luminosity, we've measured the flux. That means that we can get the distance to the star. And just to up the ante here a little bit, if we can go out and use this method that we've just talked about to measure the distances to lots of stars throughout the Milky Way galaxy, I'm just going to a Wikipedia page here on the Milky Way galaxy, the galaxy that we reside in. If we can go out and use this method to measure the distances to lots of stars throughout the Milky Way galaxy, then that gives us a way to estimate the overall size of our Milky Way galaxy. We could then in turn use that information to measure the distances to other galaxies throughout the universe, including those galaxies that are the most distant ones in the observable universe. And measuring the distances to the most distant galaxies in the universe gives us a way to estimate the overall size of the observable universe. And the size of the observable universe is an important cosmological parameter. So the stakes here are quite high. Right? We have a way here to estimate the size of the overall universe, and measuring the distances to the nearest stars in our own galaxy is an important step in that process. So I hope you appreciate how far we've come with what we've talked about in these first 4 videos. We are now in a position to do some pretty important astronomy. The pedagogical activity for teachers and instructors that I'm going to suggest based on this episode's material is similar to the one that I suggested last time in episode 3. Let me just go back to the gray star tab here. We've seen today that a star's total luminosity depends on its effective temperature, but it also depends on the star's surface gravity through the effect of the surface gravity on the radius, as we discussed earlier. So, something that you could have students explore at, say, the grade 12 level, first year university level, is to see if they can find different combinations of effective temperature and surface gravity that will produce a star of the same total luminosity. So for example, I've got this back in the default position where it's the values for the sun. Let me turn this down. This is just an example I came up with off the top of my head. If I put in a couple of nice round numbers here, say a temperature of 4,000 Kelvin and a surface gravity of 2.0, so nice round numbers to work with, and I hit the model button, I get a star of about 63 solar luminosities. Okay, now keep that number in mind, 63 for the luminosity, and let me turn the temperature up now to a little less than 17,000 Kelvin, 16,850 Kelvin. Okay, so that by itself will make the star more luminous than I just had because luminosity goes as effective temperature to the fourth power. But now at the same time, I'm going to take the surface gravity here and turn it up quite a bit from 2 to 4.5. And of course, that by itself will want to make the star less luminous, right? Because a higher gravity star is going to be smaller, as we've seen. And a smaller radius is going to want to give you a smaller luminosity by itself. Luminosity goes as radius squared. So with that combination of effective temperature and surface gravity, I'm now modeling a very different star, but notice that the luminosity comes out to being about 63 solar luminosities again, right? So that's two very different stars that both have the same total luminosity. Now, it's very hard to reproduce the same luminosity exactly as you look at different combinations of effective temperature and surface gravity, but students could try to hit the same target luminosity, say to within plus or minus 5 or 10 solar luminosities, and that would be good enough. So what students could do is they could pick a target luminosity, and I'm using 63 solar luminosities in this case just because that's how it happened to work out, but it could be any value of target luminosity that's reasonable. And then with that target value of luminosity, they could explore the range of effective temperature by trying different evenly spaced values of effective temperature as inputs. And then for each of their input values of effective temperature, they could try to find the value of surface gravity that will give them back the target luminosity that they've picked. And that would give them a data set where that data set consists of data points that are pairs of values, input effective temperature and surface gravity for that effective temperature that gives the right target luminosity. And with that data set, students could draw lines of constant luminosity in plots of surface gravity versus effective temperature. And they could do more than one line by picking more than one target luminosity and repeating the experiment. Okay, so those lines of constant luminosity in the surface gravity effective temperature plane would be interesting to look at and think about. Now, for more advanced students, maybe at the first year university level, students could even work out what the mathematical dependence is of total luminosity on surface gravity g. Okay, so in this video, we talked about what the dependence of luminosity is on radius r. That dependence is that luminosity goes as radius squared. But remember that the radius in turn depends on the value of the surface gravity log g. So students, by looking at graphs of luminosity versus log g, or really versus g, could work out graphically what the mathematical dependence is of total luminosity on surface gravity g. Now, a little trick you've got to remember here, of course, is that the surface gravity g will be 10 to the power of the log g value that's been set here. Right? That if you set a surface gravity value of, say, 2, that 2 is the value of log g. The value of g would be 10 to the power of 2, or 100 centimeters per second squared. Okay, so you and students would need to take that into account if trying to graphically determine the mathematical dependence of luminosity on surface gravity g. So after these first 4 videos, we now have familiarity with all 5 basic stellar parameters. When we come back next time in episode 5, we're not really going to introduce anything fundamentally new. Rather, we're going to put together everything we've just talked about and tie a nice ribbon around it. In fact, we're going to look at the big picture. What happens when you go out and measure these basic properties for lots and lots of stars, and we are going to introduce what is arguably the most important diagram in all of astronomy, or at least in stellar astronomy at any rate, namely something called the Hertzsprung-Russell Diagram, and you're getting a little sneak preview here. We are now actually in a position to understand this diagram, but in episode 5 we'll take it easy and talk carefully about this so that you will be able to appreciate the significance of what this diagram is and what we can learn about stars from it. And finally, I'll end up as I always do by reminding you of the main Greystar 3 website. So let me just go up here in the URL and go up one level. If you Google Greystar 3, you can find your way to the main page where there are links to a number of resources, community resources for users and teachers and developers to share ideas and suggestions. And also a link down here that you or your IT helper can use to download your own local installation of Greystar 3 if you want to use it and have your students use it without relying on a connection to a remote server. Okay, thanks, and I'll see you next time for episode 5.